office hours. Today we are going to do this warm-up question, and then we're going to move into the remaining radical material that we have. So we should finish all of chapter 8 today, which is good. And then maybe we'll have time to go into some chapter 9 nucleophilic reactions, okay? So anyone who has had or still has acne is probably familiar with benzoyl peroxide. I actually just used this in the shower. It's also commonly known as panoxyl. There's some other common names that they have out there. So it's a topical cleansing wash, essentially. And this is the structure of the main ingredient, benzoyl peroxide. So there's benzenes, and then it kind of almost looks like these esters, and they're linked together. Okay, so the first task is to ID the strongest bonds out of A, B, and C, okay? So this might even take some going back to Gen Chem to help you guys out. So remember, the strongest bonds are, the triple bonds. So remember we said that back in freshman chemistry. We had single, then double, then triple. And in terms of strength, that was strength. Just gonna draw that. Okay, so strength. I know that's really small, but in terms of strength, the single bond was less than the double bond, which is less than the triple bond, and the logic there was that there were more electrons within the bond. There are 6 electrons in a triple bond, and then that causes the attraction to the nuclei, to the left and to the right of that bond. So for instance, let's just take a look at this. Let's say this was a triple bond. That means that the 6 electrons that are in this triple bond are attracted to the nuclei here, the positive nuclei here, and the positive nuclei here. So it's a pretty strong bond. And the lesser amount of electrons you have in that bond, the lesser attractive you are to the nuclei. So the bond is farther spread apart. Okay, so basically in terms of length, it's the opposite. The single is greater than double, which is greater than triple. Okay, so maybe those are some other things to remember. So identify the strongest bond. So out of A, B, and C, clearly the double bond is probably stronger than the single bond C, okay? And then out of a carbon-carbon double bond or a carbon-oxygen double bond, which one do we think is stronger? Well, if we have an unequal pulling to one side like we do in the carbonyl, it makes it, relatively reactive. We get a partial positive there. So the fact that it's reactive means that it's not really stable. So the strongest bond is this carbon-carbon double bond where there isn't a difference in polarity. So I'm going to say A. Okay, A. ID the strongest bond is A. Okay. So the next task is to identify the bond with the lowest bond dissociation, enthalpy. So that basically says what is the weakest bond, essentially. And that's going to be, what we ruled out first. We ruled out the single bond because we knew that that was definitely weaker than the double bond. So out of the 3 options, it has to be C. Okay, and we can kind of also rationalize why. So in a single bond, we only have 2 electrons, okay, so relatively attracted to its respective nuclei on both sides, not as much as a double or a triple bond would be. But also what we have to keep in mind is that these oxygens have these lone pairs that are repulsive and kind of push the internuclear bond distance even farther. So you can imagine we have like this electron cloud, these p orbitals, sp2 orbitals and a p orbital, and essentially they're like having electrons in them and they're repulsive, so they're pushing away. So it makes this bond relatively, long, which means it's relatively labile, which means it can be broken, and has a low bond dissociation enthalpy, okay? So in terms of the free radical reaction, this is almost analogous to BR-BR, okay? This is almost analogous to the BR2-BR2 bond. You can imagine the same logic is going on. So BR with BR. The reason why we pick it is there's so many, lone pairs, and they all have these electrons in them, okay? And they're repulsive, and they're pushing away from one another. So it makes this bond actually a lot longer than you'd expect it, which makes it, since the longer the distance, the weaker those electrons are bound. So these electrons aren't bound as much. So it's easy to do that breaking, the homolytic cleavage. Okay, so that's kind of the same logic there. Whenever you have these heteroatoms adjacent to one another, it's a good idea that that's probably the one that's going to break in these free radical reactions. Okay, let's see. I think I have a chat message. Can you explain why the strongest bond is not the double bond based on the trans scan? Well, it is. So the strongest bond is the carbon-carbon double bond A over here. I hope that clarifies some things. Okay, so then after initiation with benzoyl peroxide and heat, draw one resonance structure. So that's basically analogous to saying, let me take that starting material that I provided above. Okay, and let me subject it to heat. Okay, so we already identified the bond with the lowest bond dissociation enthalpy, so that's probably, you know, this bond right here, the oxygen-oxygen bond. So we know our initiation step involves kind of using these fishhook arrows, 1 electron each. Okay, so then we get basically 2 equivalents or 2 moles of this radical. So I'll just put 2 of those, okay? And the question says, after initiation with benzoyl peroxide and heat, draw 1 resonance structure. Okay, so this was very vague. Obviously, you could draw any resonance structure, but let's kind of show that. So we can resonate like this. And oops, essentially we need these resonance arrows. Okay, so that's essentially what we got. Nothing too crazy, just a little bit of an applied question. Okay, how do we feel? Good, I hope. All right. Okay, so now we're going to move on to, I think we left off with free radical halogenation. So let's kind of just go back to that reaction for a second and discuss some main features one more time. No, I did not. I was like, I don't really need to. I realized I had enough time. Yeah. Okay, so essentially what we're going to show is that reaction one more time. So I have, this alkane, I have, Br2, and then I have, some sort of initiating source like light. Let's just say it's light in this example. And what we said was that there was 3 main parts of this mechanism. It was kind of one of our longer mechanisms. Okay, so it was the initiation step, the propagation step, and then the termination step. So let's kind of show initiation first. Okay, initiation. Okay, so essentially we have Br. We rationalized why this bond actually likes to undergo homolytic cleavage, and it's because of all these lone pairs that are on the bromine that are electronically repulsive from one another. So here's an orbital, here's an orbital, here's an orbital. These are all orbitals, and they all have electrons, and they're all pushing apart from one another. So this bond is relatively long, so I'm just going to write long bond, which means weak bond, which means low delta H BDE, which basically just means there's a small amount of energy required to break these bonds, okay? That's a good thing. So essentially, what that means in terms of mechanism, it would be Br, you can just draw, I'm just gonna draw heat in this example, it's analogous. And we draw these fishhook arrows, and what the fishhook arrows means is that 1 electron from that bond, so there's 2 electrons, 1 is retained by each fragment. So essentially you get 2 molar equivalents of the bromine radical. Okay, so you initiated this reaction by creating the main reagent, okay, Br radical, okay? So everybody kind of good on the initiation step. Okay, cool. So propagation. So propagation is at least 2 steps, okay? Propagation, at least 2 steps. But it could be more. So remember in my PowerPoint presentation that I showed about my research, like my propagation can go on for, thousands, if not tens of thousands of steps, okay? And that's how we make those long polymer chains. But, in terms of like the simple organic chemistry here, we're gonna stop after, at least 2 rounds or something like that. Okay, so let's take that haloalkane. Okay, so now we have that, that regular alkane. Okay, and let's just draw in a proton. And let me just draw maybe some other protons, okay? And we have our main bromine reagent, okay? So it's that bromine radical, okay? So the first step of propagation is known as something called proton abstraction, okay? So you're gonna remove one of the protons in these molecules, okay? So for instance, let's just say, let's actually ask ourselves a question. So how many tertiary protons do we see, okay? So tertiary, meaning a proton that's connected to 3 carbons. 1, right? Does everybody see how we only see 1 tertiary? That's this guy. This is a tertiary proton. Okay, how many primary protons do we see? Okay, 9. Anybody else? Okay, 1. Okay, so the answer is 9. Okay, so we see we have 3 here. So we have 1, 2, 3, and then it repeats here 1, 2, 3, and then repeats here 1, 2, 3. Okay, so that would be a total of 9 primaries. So 9 primaries, 1 tertiary, essentially. Okay, so just purely based on statistics. Okay, so if there are 10 total protons, right? We see we have 10 protons, and let's say 9 of them are primary. I would expect 90% of my products to be this. Okay, does that make sense? Because this step is called proton abstraction. I haven't really showed it yet, but we're going to be removing a proton and replacing it with a halogen, essentially. Okay, so you can just imagine, at this point, that the bromine radical is going to replace one of the hydrogens that we see. Okay, so purely based on statistics, based on how many protons are available, there are 9 primary protons out of 10 total protons. That gives me a 90% chance that that bromine radical is going to replace one of those positions. So I would expect 90% that, and then likewise, that gives me 10% this product. Okay, so I'm expecting 10%. So let's call this expectation versus reality. I think you guys can all relate to that. Okay, so what actually happens in real life? Well, we're not going to get exclusively, excuse me 1 second, I always get these messages. We're not going to get 90% and 10%. What actually happens with these structures, let me redraw them, is you get 100% and 0%. Okay, so that's paradoxical, right? Like why do we have that? Why do we have, based on pure statistics, 90% this structure, but exclusively 100% in real life? So there's something we have to think about. Okay, so we're going to talk about that in a second. Let's just finish this mechanism so I can prove it to you guys. So for the propagation step, the first step is one of the electrons in the carbon-hydrogen bond meeting that free bromide in space. Okay, and then the result is you get this tertiary radical. Okay, so you get this tertiary radical. Okay, and you generate HBr byproduct. Okay, but you don't have to show that. Okay, so that was the first part of propagation. So I'll just put a 1 here in parentheses. That's the first part. So let's draw the second part of propagation. Okay, so let's take that main tertiary radical that we had, and remember, it's important. You have to draw diatomic bromine again. Yes, there are more radical sources, but this is the whole point of propagation. Okay, it's the fact that we are going to keep yielding more and more radicals after subsequent product formation, and that's kind of how you show this. So we can basically show that one of those electrons meets with one of the electrons in the bromine-bromine bond, and then the other electron is retained by the bromine radical. So you can see we form a carbon-bromine bond right here. And then we're left with free bromide and radical right here. So this is the whole point. And that's the only way you can show this is if you use Br2, okay? Because then you can see that you generate free bromide that can keep reacting over and over and over again, okay? So this is the end of pretty much propagation, the 2 steps. And then termination, there are multiple different termination events you can show. But honestly, every time that you'll get it right, I just show Br, the 2 radicals, finding each other in space, and your end product is Br2, and then you ended it, okay? So let me just kind of zoom back out. What did we go through again? It was kind of like a 4-step mechanism, 3 main substeps, so initiation, propagation, termination. The initiation step, pretty easy. It's just using either heat or light to break some sort of, really, really weak bond. It's a long bond, okay? Then in propagation, the first step is known as proton abstraction, where that radical you generated from initiation is going to remove a proton, generating some sort of radical on the main alkane, okay? Then in the second step of propagation, please listen to me, use diatomic bromine, not the bromine radical, okay? And that's the reason that is you show that you're generating more bromide after you formed your product. Then in termination, you can show a couple of different things. Some people show, like you can show in theory, this one coming with let me think. You can show this with that. Okay, here I'll just show them for you guys. Okay, so let's just argue that that could also be a termination event to form the actual haloalkane. You could also say that two of these come together. Okay, so any of the radical species can come together to terminate, and essentially this one's actually weird. How do I draw this one? This one's actually that. Okay, so you actually form a longer alkane from this. But essentially, these are the main termination steps that you can have. I think the easiest one is the RBR. Yes, Mary, you have to know how to do all the termination because any of them could be fair game. Brian, yep, this is free radical bromination. Abby, does the second step propagation have a name? No, it doesn't. So the first step is called proton abstraction. You can just call the second step maybe product synthesis, if that helps you. But yeah, no official name. Okay, so let's just kind of digest that. So that's pretty much what we saw with free radical bromination. Let's take the same thing and do it with chlorination conditions and then maybe come back to why we had that weird percentage. Okay, so let's take the exact same, starting material and let's subject it to, this series of, reagents. And again, for initiation, you're just going to have the light break the chlorine bond homolytically. So you get 2 equivalents of chlorine. That's easy. Okay, now, again, same question. There are 9 primary protons. We see that, 9 primary protons, and then 1 tertiary proton. So purely based on statistics, so based on expectation, we should get 90%, and we should get 10%, just based on the number of protons that are available. But in reality, this is really weird. In reality, we get 62% and we get 38%. Okay, again, not what we expected. Okay, so for bromine conditions, we got 100% this condition, but for chlorine conditions, we kind of get skewed to the we get kind of skewed to this other direction. So something weird is going on. We need to talk about it. So clearly, we have a chlorine radical versus a bromine radical, and maybe this can, prove some things to us. Okay, so but the first thing, and I have a couple of different ways that we're going to rationalize this. Okay, and all of them are perfectly okay. So let's just draw BR. Let's draw chlorine. Okay, and let's compare. Let's make a chart. Okay, so we're here. One sec, guys. Okay, so in terms of the size of bromine versus chlorine, right? Which one is bigger? Okay, bromine or chlorine? BR, right? Bromine's bigger. So if bromine is bigger, that means it has a larger electron cloud, right? More protons available in the nuclei, right? All those things. So it's better equipped at accommodating that extra singular electron, okay? So we all can kind of rationalize that. So B, we can just say larger, which means bigger electron cloud, which equals better, better equipped for electron, okay? Better equipped for electron, essentially, okay? Chlorine is smaller electron cloud, and not as equipped for the electron, okay? For that singular electron. So this is the smaller version, okay? So that's like basically, one main way to rationalize it. And that's kind of like how I like to rationalize it. Because bromine is larger, it is more stable. Okay, so we can now say that. This is more stable, this is more reactive. Okay, so I like those words, okay? The bromine radical is more stable because, again, that electron cloud is more stable because there are more protons in the nuclei for bromine than chlorine, and the electron cloud is larger, so the electrons are more spaced out, so there's less repulsions happening in there as well. So again, this is another reason why bromine can also be said it's stable, while chlorine is reactive. Okay, so then that leads us to the next thing. So bromine would now be selective, where chlorine would probably be unselective. Let's kind of rationalize those words. Since bromine is stable, it's going to take its time when it reacts to get to something it likes. That's where selective comes from, okay? Chlorine, which is smaller and therefore more reactive, doesn't have time to waste. It's pretty reactive. So it's unselective and it just wants to get the reaction done with, okay? So that's kind of how I phrase it, over and done with. Okay, so we all kind of rationalizing these phrases. So again, bromine is larger, bigger electron cloud, better equipped for holding that electron. That makes it more stable. Since it's more stable, it can take its time when it reacts. Therefore, it's selective. Chlorine, it's smaller, which means that it's not as stable or not as equipped to handle that electron, which makes it more reactive. Since it's more reactive, we don't have time to waste. We just want to get the reaction over and done with. Okay? Are we kind of feeling okay with the comparison so far? Great. Okay, so essentially, if I now told you that the delta H BDE of the bromine radical is 46 kilocalories per mole, okay? And then the delta H BDE for the chlorine conditions is going to be 59 kilocalories per mole, if I remember correctly, okay? So you can see that the bond dissociation enthalpy for the chlorine-chlorine bond is going to be, higher, which means that it takes more energy. So you can tell right here, this says more energy to generate the radical. And remember what I said on Friday, what was so strange about that BDE thing is like the reason why we have this energy barrier, it's basically a cost to break the bond. So if I were to draw a free reaction diagram, so let's just call that, delta G, and then we can call this time. Essentially, to homolytically cleave something, it's endothermic. We know it's endothermic. You have to put energy in to break bonds, right? So this would be the enthalpy, right? Delta H, BDE, because this is my reactant, and that is my product. That's my enthalpy, BDE, and we know it's going to be endothermic. But essentially, if the delta H BDE is a larger value, it's 59 kilocalories per mole, and then delta H BDE for bromination is 46. So maybe let me draw that. Okay, so then this one would be, maybe let's just say that would be for chlorine, and this is delta H BDE for bromine. So notice how the activation energy, is less for bromine than it is for chlorine conditions. So, and also notice the energy levels of your products. The energy level of your chlorine product is up here, whereas bromine is down here. So chlorine is higher in energy, more reactive, more unstable, unselective. Bromine is better. Okay? I think we kind of did a good job there. So now that brings us to our first types of questions, and why do we have this scenario? Okay, so let's take, let me just take this example. So I'm going to take this example, and let's just do this. Okay, so first I want to show bromination conditions, and then I want to show what happens under chlorination conditions. So under bromination conditions, essentially we know we're generating this main reagent, this bromine radical, right? And that bromine radical is going to be very selective. We talked about that. It's very selective because it's a more stable radical, okay? So it's going to take its time when it's reacting, and it's selective for the proton that's at the more substituted position. And the reason that is think about it. We know that the first step in propagation is known as proton abstraction. And what happened in proton abstraction? Well, I'll remind you guys, you generated a radical on the main alkane chain. Okay, so bromination is selective, basically in this first step, to position itself where when it removes the proton, that radical forms at the more stable position on the alkane for reasons we've all talked about, like hyperconjugation and resonance and things like that. So in this option, in this starting material, the most stable position is the secondary benzylic position. okay? Because we have, resonance, as well as the fact that it's pretty decently hyperconjugated. So that's the most stable position. So essentially, you can imagine that the bromine radical is going to do proton abstraction here, okay? So the main, intermediate, so these are radical intermediates now. It would be this guy, that main radical intermediate. We can resonate with the benzene ring, which makes it pretty stable. So that means that now the bromine is going to come in and add at that position, okay? So we would expect, Br again, Br, I'm just showing the propagation steps, and you get something that looks like this. Okay, I put a star. Okay, so I just showed the two propagation steps, essentially the proton abstraction step, and then the main, product synthesis step. Something you need to keep in mind, though, is even though we said carbocation stability and radical stability are parallel to one another, the same logic in terms of, electron molecular geometry applies, because carbocations are sp2, radicals are also sp2. So we went from sp2 to sp3, so we definitely have a stereoisomer thing to consider here. We need to consider the bromine adding on the top face of this p orbital or the back face, and then we would essentially get two major stereoisomers from this reaction. So this is the products under bromination conditions. Okay, Lula, good job. And Leah, so secondary plus resonance is better than tertiary. Yes, it is. Secondary resonance, something like that. Yep, thank you, Abby. Okay, so that is the products under bromination conditions. Okay. So chlorination conditions essentially states that, we're not selective. We could form a mixture of different products. So, like we saw with those experimental percentages, look at this. So for bromination conditions, we exclusively get the more substituted product for reasons we've talked about. Okay, so every time we have bromination, we are going to form that haloalkene on the more substituted position. Okay, but in comparison with chlorination conditions, we actually get a mixture of all products. We get the more substituted position, and we also get all the unstable positions as well, for reasons we've talked about. Chlorine is smaller, which means it's more reactive, which means it's higher in energy on this diagram, which means it's unselective, okay? All of these things. So let's go back to, this main example that we're doing here. And basically, anywhere you see a proton, with the exception of the benzene ring, you can imagine a chlorine product will form there. So essentially, this could be one. So we could get the same exact example that we saw before, where we had a racemic mixture of the more substituted position. But you could also claim that, what about the proton that's in here? Okay, that works. Oh, no, excuse me, not bromine, chlorine. Or what about even the protons up here? Or did I not do that right? Oops, only one of these. Okay. But what about the proton up there? So you actually get a mixture of 4 different products, and these would be all 4 products, okay? We're not actually going to remove the protons from the benzene ring. They're pretty strongly bound, okay? So don't touch the benzene. Remember, never touch the benzene, okay? So that's the difference between, free radical bromination and free radical chlorination. Sorry, I got a Zoom call, FaceTime call. Okay, what's the difference between free radical bromination and free radical chlorination? The fact is that the bromine is more selective and chlorination is not as selective. So for predicting your products, bromination needs to be every single major product, whereas chlorination is every single product. 1 second, guys, just responded to a message. Okay, Leah, so if there's a secondary radical resonance even on the more benzene ring, that will be more stable too. Yeah, I want to go with yeah. Yes, the CL's on the tertiary, yeah. Okay, cool. So let's just do some examples in the student workbook. So we're on page 93. Well, we just showed kind of A. We just did A, the bromination version of that. So let's just do B, okay? So now I guess we're on page 94. So it looks like this. Cl2, light. Essentially, we know chlorination is not selective, so we can get, maybe it adding here. We could get it maybe adding here. We could get the dashed version of that. We could also get it adding here. okay? And we're not going to show them on the left side because it's a symmetrical molecule. So again, these would be the 4 main structures. Pretty easy. Just think about everywhere there's a proton and where you're not repeating a structure, and also always keep in mind your chirality issues, okay, in case you generated a chiral center. Okay, so these would be my 4 products, and that's it's as simple as that. Okay, let's look at C. Okay, so for C, I'm telling you, I really think this chapter is pretty easy. Okay, so bromination, we know we're going to find the more substituted position. I see a tertiary. Okay, it's not symmetrical, so I have to consider all stereoisomers. Done. Okay, do you see how fast this is? Caroline, is there one at the end of the methyl substituent? From which one? Oh, yeah, wow, I didn't see that. Yeah, that's not symmetrical, that could work. Yeah, that works. I don't see an ethyl version. Yeah, thank you for catching that. I didn't see that one. Leah, this may be a stupid question, but if there's already a chiral center where you add the chlorine. Okay, interesting. I like that question. I'm trying to think of like a way to draw that. Okay, so are you saying, let's take this example that we saw above, and let's make this already a wedged methyl group. It's basically what you're saying, right? And are you asking what happens to that stereochem? Great. Okay, great question, actually, and this is pretty cool. So essentially, right now, what's the configuration in terms of R and S for this structure? What do we think? R and S, not sp2. This is sp3. So this is R. Yeah, R. Good, everybody. R. Okay. So what's the main intermediate, right? What's the name of that main intermediate we're going through? It's not a carbocation. It's not one of those bridges. It's a, which is an R. It's a radical. Radicals are what? Hybridization. sp2. Great. So let's go down to that radical. So we know we're going to go here in the middle of the mechanism. Okay. And we went from how many areas of electron density? Okay, that's 3. So that's sp3. And then here, 1, 2, 3, sp2. sp2 is planar. We have that unhybridized p orbital. So what happens is you actually have an effective loss in stereochemistry. Okay, so we lost stereochemistry. So the R now goes away. The molecule doesn't remember what it was. And now we can get both R and S enantiomers. Okay, so it's actually interesting. It doesn't matter. You actually lose the integrity of that stereochemistry in the starting material, especially if it's at the molar substitute position. Okay, so you can see that? It doesn't matter what, that's why we actually didn't even show it to you in the beginning, because it doesn't matter. Yes, yes, you can. I'm just I'm having trouble imagining how you would form a carbocation intermediate that was chiral, like, you know what I mean? Like all the carbocations we've seen have come from pi bonds. So essentially, you know, I'm imagining something like that. So you go from sp2, to sp2. I haven't seen an example of going from sp3 to sp2 with the carbocation, but I see where you're going with that. Okay, keep going. Let's do D. So D would look like this, okay? And we're doing this under chlorination and heat. Okay, again, I think about every single place that there's a proton, keeping in mind symmetry. So I'm thinking probably at the end, I'm thinking, I like this version, I like that version, I like this version, but remember that's a chiral because the left and the right side are different. Yeah, so now things can get a little bit tricky in terms of how many stereoisomers you have. We could have the chlorine adding there. You could have, you know, I'm just going to draw star. There's so many. You can draw it there. You can draw it in the And I think that's pretty much it. And then for these, there are 2 each. I'm not going to draw them all out, but essentially there's wedge, 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 dash, dash, wedge. Actually, are there 4 of these? Yeah, exactly. So on the test, you would basically have to be able to recognize which ones are possible. No way are you going to have to click every single one. I think there might even be 4 of these, not 2, because you could get the trans, the cis. Well, some of them would have 4 and some would have 2. This would have 4. This would have 4. This one would have 2. Yeah. So look how many of those are. That's 8, 9, 10, 11, 12, 13. That's 14 structures. All right. Okay, Ryan, do the CL on the on the tertiary carbon of stereochemistry. Oh, you got it. Okay. On the tertiary, it does not have stereochem. Okay, so just keep in mind that like literally every position could be reacted with, and that's just something to keep in mind. All right, and then E. Okay, so we have Pearson drew a line in between to show that symmetry. That helps so that you don't repeat any products. Yeah, that's important. Make sure that you don't repeat any products. So we're here. So, oh, that's not a proton. That's a methyl group. Okay. So essentially we have Br2 and light, and you would instantly think to go to this methyl position, but how many valence electrons are there? Already 8. So 2, 4, 6, 8. So there actually is no proton there to react with. So you are kind of forced to go to one of these protons over here. Okay. So essentially we know that we're going to go through that radical at that position. Okay, so that's this, and then you can get major diastereomers of that. So you can get either this diastereomer or this diastereomer. Okay, pretty easy. And that's it. Okay, so that's the first reaction, you know, and now we have 2 more reactions to cover in the chapter, and we'll be done. Okay, how do we feel? Decent? Take a second, let that digest. Yeah, I like it too. I don't think this is actually a nice chapter for you guys. Okay. Not bad. Good. Because the next chapter, you're going to be saying the exact opposite. It's a bit like that. Chapter 9 is notoriously the very hard chapter out of all of organic. So, yeah. But we'll get you through it. We're going to do a lot of practice. Chapter 9 really is the hardest one. I'm not going to like sugarcoat it. Everyone, it's the hardest one. But it's okay. Don't freak out. You got this. Okay. So the next so we basically have seen free radical halogenation. Okay. So now we're gonna have something different. So this is called free radical addition of HBr. Okay. So it's kind of like a very specific name. So before we had free radical halogenation, so we're just halogenating these starting materials. Now what we're going to do is we're going to subject these, you know, pi bonds. Okay, so now we have again these alkenes. So it's weird that we didn't see this in the alkene chapter. Okay, so let me just say some maybe just our generic example that we've seen so far. So we have some sort of alkene starting material, and we do have hydrobromic acid. Okay, so far this looks pretty similar in terms of what I've seen before, right? This is hydrobromic acid. And you would think that this undergoes hydrohalogenation, right? So let's just draw halogenation, you know, mechanistic arrows. Okay, remember it follows Markovnikov's rule. Okay, we get that tertiary carbocation, Markovnikov. That's a tertiary carbocation, just keeping you guys in check, remembering all the things that we know. And then that means we generate free bromide, and that free bromide can come in and attack that electron deficient center. Okay, so that was, you know, hydroboration. It was hydrohalogenation. Okay, so now let's say I take that same starting material. Okay, let's say I take that same reagent, but now I also put it in the presence of heat and some sort of, I'm going to call it ROOR for now. Okay, so some sort of peroxide. Okay, so essentially this is the first time that we see a peroxide as a reagent. Okay, so what happens is we have to again gauge what is our main reagent coming from this line of 3 different things. Okay, so let's kind of show that. So initiation in this step actually is the 2-stepper. So let's just try to remember where we are. So for free radical halogenation, it goes, let me just draw this down here maybe. I'm going to call it free radical halogenation. And then this one I'm going to call free radical addition. Okay, so do we see that? Free radical halogenation, free radical addition. Okay, so under free radical halogenation, we basically had, in terms of initiation, here, let me just actually call it I, propagation, termination, and all of that. The initiation step was 1 step, okay? But now the initiation step is going to be 2 steps, okay? And then the propagation step was 2, okay? And also the propagation step is still going to be 2, okay? And then the termination was 1, and this was 1, okay? So something to keep in mind is that the key difference here was that the propagation step is always 2 steps, okay? Here, let me just say it was called the first step, maybe the first one was called the proton abstraction step. I'm just trying to give you guys like a little roadmap. And the second one was like the product. Maybe something like that. This is product. Okay, so let's just kind of go over the mechanism. So for initiation, we're expecting 2 steps. So that's kind of the main difference here, is we're getting 2 different steps. So let's take, so you might see something called ditert butyl peroxide. We commonly call that as toot, like toot, because it looks like this. Okay. So that now you guys can probably see why we call it toot, T-O-O-T. It's ditert butyl because that's a tert butyl group on both ends. Peroxide, okay, ditert butyl peroxide, and that's kind of, sometimes we abbreviate that as ROOR, meaning alkyl, oxygen, oxygen, alkyl. Okay, so it's kind of the same exact thing. So let's just take the ditert butyl peroxide example. So essentially, the first step we can imagine is, you know, homolytic cleavage of this peroxide with heat. Okay. So pretty easy. And you get 2 molar equivalents, so nothing new yet. Okay. And then basically we can take that main radical and then react it with HBr, hydrobromic acid. So far this kind of makes logical sense. You know, we had an extra reagent, so we might have an extra initiation step. So now you show this. This is where proton abstraction actually is happening. Okay, so this is weird. So this is one example of proton abstraction. And the whole goal of this step is to generate bromide radical. So we generated tert-butanol. So this is TBUOH. Okay, so that's the alcohol version, tert-butanol. And we also generated free bromide. Okay, so this was also proton abstraction. So some things to note about. So there's step 1, step 2, and that was proton abstraction. Okay. I don't know. So essentially that's initiation for this main reaction, okay? And then in terms of propagation, now we have to bring in our main alkene propagation. So we have this, okay? And then we have our main radical. Okay, so now this is kind of like the key reactive step here, okay? So what's going to happen is that this radical is going to react with the pi bond, the 2 electrons in that pi bond, okay, such that we form some sort of intermediate where the radical is on the more stable position, okay? So that's basically following Markov-Nikov's rule. So let's think about that. This 2 electron bond, one of those electrons is going to come and meet that 1 electron of the bromine and form a carbon-bromine bond. But that extra electron that's retained in this pi bond is actually going to go on the more substituted position because that's the more stable position. Okay, so essentially you form a tertiary radical where the bromine was added on the less substituted side. Okay, so you guys kind of see that? So essentially this was the main key step here, was once we formed that bromine radical, and specifically with a pi bond present here, the radical was formed on the more substituted position, forcing the bromine on the less substituted position, okay? So then there's one more propagation step where essentially you take that, you know, intermediate structure, you have HBr, you know, byproducts laying around, and remember, you always have to use HBr. You don't want, or Br2, you didn't want to use another equivalent of the radical. And you grab the proton, so this is another proton abstraction. So there are 2 proton abstractions now, you can see. So again, 1, 2, and that was proton abstraction. Okay, and then you're left with this product. So the key difference I think I want to point out is that when we did hydrohalogenation, look at where the halogen went. It was Markovnikov addition. Then, now when we do this peroxide version, we're able to get anti-Markovnikov addition of halogens. Okay, that's really important. Okay, and then termination, I'm not even going to go over. It's just remember the two radicals coming together. Okay, how do we feel? So again, all you need to know in terms of the product is you're going to form, less substituted haloalkanes. Excuse me. All right. Decent, maybe. What is the point of termination? It ends a reaction. So for instance, if we were to go back to, my chemistry example, where with my lab, I could theoretically make radicals, my polymer chains build on forever and forever. But the problem is that as my chains get longer and longer, it becomes heavier and viscous. So think about it, like my solution basically goes from a liquid to like a gel to a putty to like a solid, essentially over time as the polymer gets longer. So let's say like I don't want to make, a rock solid polymer. I want to make a gel. Like that's the purpose. I want to use this gel on like the human body. So if you want a gel, you have to be able to terminate or stop at a specific point in my reaction. And the way to do that is to throw a whole bunch of radicals in there, and then they terminate with one another and it ends. Okay. So in real world, it has huge implication. What is the point of termination? Well, and to stop those reactions from progressing. Like, how come you think why is your plastic water bottle like relatively thin and like you can compress it, whereas there's those big plastic carboys of water, like 8 gallons, and those are pretty thick. They're different molecular weight polymers, and they progressed farther in different reactions. Pretty cool, if anyone cares. All right, so that's that reaction. We got 10 more minutes to go over the last one, and we'll be done. So essentially, let's do a couple examples of this. So for F, we're on page 94. Okay, HBr, ROR, heat. Okay, so we have a tertiary position, we have a primary position. What's happening is we're having anti-Markovnikov addition. Excuse me, this was secondary. We're having anti-Markovnikov addition, so we should expect products. Okay, products there. And then we have 4 major stereoisomers to consider. Wedge, wedge, dash, dash, wedge, dash, dash, wedge. Okay? I'm not going to draw them out, but essentially you can imagine that. Okay? So for G, we have this, and we have that, and we have HBr, ROR, heat. Okay? Again, tertiary, this is secondary. We know we're adding on to the less substituted side, so we're going to get that, and again, we're going to get 4 major stereoisomers here. Okay, 4. Okay, H. Okay, and this time we're drawing it out. Okay, so that's 2. So we have with respect to the alkene, we have the secondary or the primary, okay? Excuse me, tertiary or the primary. I'm all over the place today. So clearly this is going to add on the primary position, okay? So we're thinking something like that, okay? But in the process, you became chiral here. So you need to draw these. Okay, those are the 2 products. And one more. So I'm gonna leave the last one for you guys to do. So. And this is hydrogen peroxide, okay, like you put on your like boo-boos or things like that. So we have a secondary position and then the secondary position. So really there is no main difference here at first glance, but then you realize that this isn't only any secondary, this is secondary benzylic. So yes, this is the less substituted side in terms of stability. So we're going to form that, okay. Yes, hydrogen peroxide is that main initiating thing. So instead of it being, you know, diterbutyl peroxide, it was that homolytically cleaving to get 2 hydroxide radicals, and then the 2 hydroxide radicals reacted with HBr. So it would be something like this. So you get water, and you get free bromide, and then the free bromide reacts with the, you see how this is going. So then the bromide comes here, and then gets that, goes there, yada, 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 keeps going. Well, that's not right, but you know, as you know, fast. So yes, the hydrogen peroxide just takes the place of the ditetrobutyl peroxide. All right, we got one more to go, so let's finish that reaction, and then I'll let you guys go. So this one is called the Lilac Bromination. Some key things we have to think about here is some resonance arguments. So something you need to know, another Lewis structure is N-bromosuccinimide. So this is NBS or N-bromosuccinimide. If you want to know where this name comes from, succinate or succinic acid or whatever, that's a main citric acid cycle intermediate where there's 4 carbons, so 1, 2, 3, 4. Amide at the end comes from the fact that this looks like an amide functional group. N is just in the front to tell you that the bromine is connected to the nitrogen and not to a carbon. So N-bromosuccinimide, so it's basically the succinic acid version. So it's the succinic acid derivative. The amide it's been converted into an amide, not an acid, and then the bromo is coming off of the N. So N-bromosuccinimide or NBS, essentially. So the main, obviously, if you were to identify, this is an important, kind of what we did today as a warm-up, what is my weakest bond in this structure? Okay, let me just label things for you. How about this? A, B, C, D. Out of A, B, C, and D, which one is my weakest bond, or the bond that has the lowest bond association at the P? Okay, I see D. Yeah, D is a good answer. Okay, because again, remember those electron clouds. Those lone pair electrons are repulsive. They push those spaces far apart. So yeah, D is definitely a good option. So again, you can imagine that the products of, and we don't need to know this in terms of mechanism, at least not to my knowledge. You get a this radical, so this radical on the nitrogen, and then you also get this bromine radical. And that's interesting is like why was this reagent used in the first place? Well, A, the identity of the atom that bears the radical is the nitrogen, not a carbon. And C, look at the resonance that's possible with the carbonyls. So this is a pretty stable structure. That's why this is pretty chemically liable. Okay, so we generated this radical and this radical. And essentially, what we're doing with the, I don't think we cover the full mechanism. She didn't go over the mechanism, right, with you guys? Yeah, I don't think she does. She just goes over key points. Yeah, okay, so there's no mechanism to know, which is good. But essentially, let's just take an example. So let's take this, and let's just do NBS and heat, okay? So essentially, what you need to immediately go to, because we don't cover the mechanism, is knowing that this goes through the intermediate known as an allylic radical, okay? And you guys know what allylic radicals are. So allylic means adjacent to a pi bond, okay? And radical, okay? So adjacent to a pi bond is here, okay? And then you guys put a radical. So the main intermediate is this, okay? So once you have gotten to that intermediate, and we don't need to know necessarily why, once we're there, you have to consider resonance structures, okay? So let's draw resonance structures with this pi bond. So ready? 1, 2, 3. Those are my resonance arrows. And that would be the resulting structure. So this is A, and this is B. And let's kind of just talk about some things. Okay, so in terms of the radical, let's consider the radical in structure A, okay? What is the substitution of that radical? In the chat box, if you guys can. Secondary, right? Secondary. Okay, and structure B, what is the substitution of that radical? Primary, great. For the alkene in structure A, what is the substitution? I'm looking for mono substituted, di substituted, tri substituted. Great, mono substituted. Okay. What's the substitution of the alkene in structure B? Di, great. Okay, so now let's think about each one of those rows in isolation. So for radicals, which one is more stable, A or B, just in terms of radicals? A. Ooh, okay, we got some B's in there. In terms of which one is, oh, I think you guys were confused on my overall question. But in terms of just the plain radical, it looks like structure A is better. So I'm going to circle that. Okay. Then in terms of alkene stability, we know the more substituted that alkene is, the more stable it is. So clearly disubstituted seems better. So which one wins? Is it radical stability that wins, or is it or is it alkene? And clearly it's alkene. Alkene substitution outweighs radical stability. So essentially what we did was we were just considering any possible resonance with this alkene that we could get a new intermediate where we had an arrangement possible. So this is kind of a version of a carbocation arrangement. This is just a alkene rearrangement. Okay, so alkene rearrangement. Okay, and then because this alkene is in the more stable position, this is a better intermediate, and then the bromine is just going to come in and add there. Okay, so that means that your end product is this. Okay, the bromine just adds there. So that's kind of the key mechanistic points you need to know for your mechanism. You don't need to know anything beyond that. Okay, so you have to know which bond is the weakest one. It's the N-bromine bond, obviously, for reasons we've talked about. We go through this allylic radical, okay? And then you always have to check, once you form that allylic radical, is there resonance possible such that I can move this alkene to rearrange into a more stable position, and then the bromine can come on and add, okay? Exactly, this is minor products. So you would say probably like 90% this product, and maybe 10% minor that. Okay, yeah, it's just a minor product. Okay, so let's take an example of that, okay? And then we'll be done. We have 1 more minute, so I'll just do one example. Okay, so let's just look at K, and we'll be done with chapter 8. So I told you guys we can finish. Okay, so NBS and heat. We know we're going through an allylic radical. Okay, clearly there are 2 allylic positions. There's allylic position A, and there's allylic position B. Both are adjacent to the pi bond, okay? Now, you have to use a little bit of your brain here, okay? Which one is smarter to pick? There's always going to be a smarter choice to pick. A, okay? I'm glad that some of you guys are seeing that already so quickly. It's obvious to click A because at A, there's a more stable position and a less stable position nearby. For B, there is no difference. Like, there's no reason to go to the B direction. It's not going to help you. So for me, I would think to assume that the allylic radical forms on position A, okay? So there's always an obvious one and a non-obvious one. And then resonate with that one to get this, okay? And then now you see that we went from a di-substituted alkene to a tri-substituted alkene. So then the bromine can just add where that radical was on the main radical. And remember, you have 2 main diastereomers there, okay? 2 main diastereomers, okay? 1 second, Caroline, I can answer your question in a second. Okay, wait, can you explain that again? Some more stable tertiary and less stable secondary position nearby. Okay, there's always an obvious, what I meant was there was always an obvious position, and that was A, because if I were to resonate this pi bond to the A position through that radical, you go from clearly di-substituted to tri-substituted. But if I were to resonate it to like this B position, you only go from di-substituted to di-substituted again, okay? This methyl group is too far away. So there's no reason to pick the B allylic radical because you're not going to change your substitution of the pi bond. That was like the reason why we said that. Maybe let's just do one more example. So like the same exact thing happens here, like in L, I believe. So there's an obvious one and then an obvious one. So NBS and heat. Okay, so 2 allylic positions. Here, A, and here, B. Again, there's a very obvious one and not obvious one. It's A. A is obvious because like you can resonate to the right and go from di-substituted to tri-substituted. But if you were to resonate down to B, then it's di-substituted to di-substituted again. Stupid, okay? So we basically want to imagine that we're going from that radical, and then you resonate and essentially you get your bromine adding there and you get two main diastereomers. So you would get that. Okay, and that's pretty much it for this chapter. Yeah, that's it for radical stuff. So basically on Wednesday, we'll probably just do some of the critical thinking as a warm-up, and then from there we'll move on to chapter 9. And chapter 9 is going to be pretty tough. So don't worry, just make sure you can know all of chapter 8 going in, because you guys will feel good having at least that whole chapter secured under your belt. And then we'll go into chapter 9 material fresh and, try to pick it up piece by piece, okay? And there's going to be a lot of extra supplements as we start going into the next 2 weeks. I have a whole bunch of extra documents and extra word practices, extra practice problems that I'll be sending your way, because definitely one of the more tedious stuff, okay? With that, see you guys. Good luck. Keep it going. Peace.